Uh, the C part is a partially fixed pile head. Okay, in a fixed pile head, the pile undergoes some rotation at the joints of their head and the cap. Okay, means here some partial rotation is taken place. Okay, so these are called as a partially fixed pile. Okay, so following the same equation earlier for a fully fixed pile. Okay, so partially fixed means here we are allowing a some partial fixed factor. Earlier this value was supposed to 1, that means fully fixed, and now this lambda is introduced, which will reduce the value less than 1 for a partially fixed the pile. So lambda value varies from greater than 0 to 1. 1 means it is a fully fixed pile. Okay, so the value varies from greater than 0, less than 1, and when we consider 1, it is a fully fixed head. When we consider 0, so this term becomes 0, so then it is a free head. That is how a partially fixed pile head is slightly different from the your fixed pile. Now we'll solve some numerical based on this theory. Okay, so up till now what we have studied, just we'll take a recap, is that we have gone through the different expression, that is for a free head condition. First, in a free head condition, various the expression which we are written, okay, right from this. One is for a deflection equation. Okay, then we studied the moment equation, slope and the shear force equation. This is why by considering a free head condition, and then we have seen the how different coefficient, A coefficients and B coefficients are obtained with respect to the depth. Then we talk about the relative stiffness factor, how T is calculated, and then we discuss about the fixed head condition. When fixed head condition, slope is not allowed, how you we get a counterclockwise movement, okay, to keep this slope 0. Mg is equal to minus 0.93 Qg into T. And we discuss about the deflection equation. Then we discuss about the moment equation for a fixed head, and similarly for a partially head by introducing a lambda. Okay, now let us solve some basic simple numerical initially. Let's see a concrete pile 50 centimeters square size and 8 meter long, total 8 meter long, is subjected to a horizontal load Qg of 5 kilonewton and a external moment of 4.5 kilonewton meter at the top or ground level. Then coefficient of subgrade reaction is given 2 × 10⁴ kilonewton per meter cube, and here use determine the deflection. First part, if head of the pile is free. Second, the head is considered to be fixed with no external movement. So the as a cross section is given, so first part will try to find out this T is relative stiffness factor. So for that we require EI. So a size is given, square size, so we can quickly find out moment of inertia, BD cube by 12. 0.5 is the size, 0.5 meter, so we get 0.0052 meter or 4 I value. E value is given 3 × 10⁷. Okay, so find out EI multiplying these two, so we get 1.56 10⁵ kilonewton dash meter square. Now find out the relative stiffness factor. Okay, its unit comes out to be finally in a meter. Okay, so T is equal to EI upon NH. EI value is calculated here. NH value is given 2 into 10 raised to 4, and the ratio and power is 1 upon 5, so we get 1.508. Now this method is applicable for a long pile, so let us check for the whether it is a short or long pile. So you can check it like this: Z max is equal to L by T. The length is given 8 meter, T is given 1.508, so you get 5.305. So it is greater than 5, means it is a long pile. Also it can be tested other way. L should be greater than 5 times T. Length is 8 meter. 5 into 1.508, so it is 7.54. Length is 8 meter. So it satisfies that it is a long pile and theory is applicable for a long pile. Now to find out a deflection, first part, maximum deflection. In a free head pile, maximum deflection takes place at the ground surface. Z is equal to 0. When Z is equal to 0 from the table, AY is 2.435, BY is 1.623 from the table. So substituting the values, maximum deflection YA plus YB. So substituting these values, AY, BY and QG value, phi is given, moment is also given. It is a free head case, so moment is given 4.5 divided by this EI values. So substituting this, converting in mm, 0.374, very negligible value, maximum deflection. Okay, now find out the moment at the pile head. It is, suppose the second part is asked moment at the pile head for same free head condition. Okay, now you can see the AM moment we write as AM QGT plus BM into MG. Okay, you know the AM value in a table, if you refer, it is a 0, and BM value is a 1 from the table, as Z is equal to 0. It means it is equal to the external moment. Substitute here, it is same as the 4.5. Now maximum bending moment for a free head condition. Now the depth at which the bending moment is maximum is not known, because the variations we have seen earlier in a very beginning part, that how it varies. You can see the moment. Okay, so we don't know where exactly it is the maximum. Okay, so therefore we write the equation, the same equation, mx is equal to am qgt bm mg. Okay, and to find out the these two parameters are we have to investigate from the table. Let us see. So the final expression is 7.54 am plus 4.5 bm. Okay, so now substituting am and bm values for a different z and the depth at which mx is maximum, so we get the equation mx is equal to 7.54 am and 4.5 bm. Now this am and bm value will substitute from the table, and we'll check the moment at a different depth, and depth at which this moment is maximum is the maximum moment at that particular depth. Okay, so here, so you can see this table. These are the same values obtained from the table, varying from 0 to 5, first interval up to 0.1, 1 and then 5. Okay, these are AM values from the table. Okay, then BM values, because we required a MX for a different depth. And what was the last equation was this 7.54 AM plus 4.5 BM. Okay, so this AM multiplied by 7.54 and BM multiplied by 4.5, so you get total, and this total are given in the last column. So this combination is a maximum. You can see here the moment it goes on increasing here as x increases, and at 1 z is equal to 1, it is maximum 9.32, and then further decreases. Okay, so it means the moment is maximum at 1, that is mx. Okay, and it is therefore mx is 9.32 kilometer meter at z is equal to 1, where z is x by t. Therefore x is calculated as uh, z is 1 and t 1.058. So it is at a depth of 1.508 from the ground surface or pile head. Okay, so this shows if you plot this curve, you will get a deflected, you will get the bending moment curve. Okay, and then the next part of this problem is the a fixed head pile. When head is fixed, you can see here the theta is 0. Okay, so this is the same expression. So mg is equal to minus 0.933 qgt. Okay, and so maximum deflection is given by y plus yb. Okay, so for fixed head condition, the y max is taken as ay minus 0.93 by qgt cube of ei. Okay, now here at z is equal to 0, the ay value is 2.435, by value is 1.623. So you get a deflection as, now here when you substitute this is in terms of a qg, because there is external moment here, but this is the counterclockwise movement. That's why that m value will not take 4.5 will not be takes place here, and here we substitute the qg value. Okay, so substituting the values, that is 2.4 at z is equal to 0 and 1.6, so we can find out the maximum deflection, which is deflection is maximum at the surface. So we get maximum deflection is 0.101 mm. Now we'll go for the another example here. A 600 mm RCC pipe circular is driven into the loose sand. So 600 mm RCC pile, this is a circular pile driven in a loose sand for 20 meter. So L is 20 meter, diameter is 0.6 meter in under a submerged condition. Calculate the ground line deflection, means the deflection at the ground surface of pile under a lateral load of 268 kilonewton at a ground level under a free head condition. Okay, so here you have to find out the deflection of pile under the given lateral load. Okay, in free head condition. The M35 grade of concrete is it was used for casting, and take the coefficient of subgrade reaction is 6 mn per meter square. If the pile is subjected to the lateral load of 268 kilonewton at 2 meter above the ground level, what will be the ground deflection? So this question is asked into two parts. So in the first part, we'll see length is 20 meter, diameter is 0.6 meter, and this coefficient of subgrade reaction is given 6 into 10 raised to 3. Free head condition is given, and first calculate, because we have to find out the relative stiffness factor. So for that we require the E value. So E value is taken as 5000 root FCK. So grade of concrete is 35, that is in MPa or Newton per mm square. So you get this E value in Newton per mm square or MPa 29580. All our values generally we keep it in the kilonewton per meter square. So I multiply into 10 raised to 3 again. So it will be 2.9580 10 raised to power 7 kilonewton per meter square. Okay, calculate I value at this circular section, pi d power 64. So diameter is 0.6, so you get I value 0.00636 meter 4. So you get EI finally 188,179.81. Okay, now calculate relative stiffness EI upon NH. Okay, and substituting this value of EI and NH for 1/5, you get this value is 1.997. So it is 2 meter. Okay, now first part is you have to find out what is the y now under a load of 268 in a free head condition. Now here there is no external moment given. Okay, now first we have to test whether it is short pile or long pile. So we can calculate z max L by t. Length is given 20, t is 2, so it is 10, means greater than 5, or in this way also. So it is a long pile. Therefore ground line deflection, the deflection is maximum at the ground surface, and for free head condition no moment is given here, and it is a free head. So therefore y is equal to ay qg dq by ei. So here y is unknown. Okay, qg is given to 68, ei value is calculated. So from this we get yg. The deflection at surface is 27.74 mm. Now the b part, what the b part says that if the same load is subjected, that is 268 kilonewton at 2 meter above the ground level. Okay, so above the pile tip the load is acting 2 meter, so it act like this. So the load is acting at 2 meter, so it exert a moment also in addition to the load. So load is 268 kilonewton, that will be the same here, and the moment 268 into 2, 536, sorry, it is kilonewton meter. Okay, so the moment is calculated. Now substituting in the equation y at ground surface, because the deflection is maximum at the ground surface, so at z is 0, so we are writing yg, that is ay, and in terms of ay for qg and by for mg. And now substitute the equation, substitute all values here. Okay, and you can calculate the deflection, that is here 46.23 mm. Okay, so in this way the deflection is obtained for when the load is applied at a certain distance, that is here it is 2 meter under the free head condition. Okay, now okay, now we'll go to the another numerical here, and the probably this will be the last numerical. Okay, here 20 mm thick and 280 mm inside diameter steel pipe. So it is a pipe. Okay, it means its internal hollow diameter is 280 mm and the thickness of pipe is 20 mm, and it is 20 meter in length, installed as a friction in situ pile with a steel bar M35 concrete. Means it is a with a liner. This pipe is called as a liner, along with a concrete as a RCC. The steel cage is inserted, and then it is casted with a M35 concrete. Okay, the E value for a steel as 200 GPa is given, and coefficient of subgrade reaction is 5560 kilonewton per meter cube. Okay, so this is a hollow pipe or liner, which is actually a bottom is close end, and it is casted as a RCC. Okay, calculate allowable lateral load for a maximum 7 mm deflection for free head HEAD free head pile. Okay, so let us will go one by one. First part, allowable lateral load for a maximum 7 meter. So here deflection is given and we have to find out that load. Okay, now it's a composite pile, consists of steel and concrete. I can show you like this. This is a steel pipe, close end pipe called as liner, 280 mm internal diameter, 20 mm thick, and this is filled with a concrete and RCC reinforcement inside. Okay, So this composite pile consists of both steel and concrete material. Therefore, transform the section into a equivalent single material. Okay, so it means this composite we can transfer into a single equivalent concrete piles. So we are replacing this steel with the equivalent concrete diameter. So equivalent single material, convert the steel thickness into the concrete using a modular ratio. In your mechanics of solid, you must have studied that thickness of concrete, the ratio is written like this. It is like inversely proportional here. Tc upon Ts steel, thickness of concrete to thickness of steel, inversely proportional to their modulus steel to the concrete. Okay, therefore thickness of concrete, equivalent thickness of concrete, replacing the steel as Es upon Ec into thickness of steel. Okay, so we required a concrete to find out the E value of the concrete. So 5000 FCK is the, as per IS 456, okay, the modulus of elasticity of the RCC component, RCC structural member can be obtained. So this is in a MPa or a Newton per mm square. Okay, so we get 29580 MPa. So multiplied by we'll keep in KPa. So multiplied by 10 raised to 3, 2.95804 10 raised to 7. Okay, so this is how we get the E value. Okay, now this E value will substitute here. Here, and steel E value is given 200 GPa. We can calculate equivalent thickness TC. So this E value also we can write in terms of a GPa. If I divide by 1000, then I get this value as 29.58 as a GPa, because this is also given in GPa, easy to substitute in this ratio. Okay, so concrete value we again converted into the GPa, and then thickness of the concrete, equivalent thickness 200 by 29.50 into thickness of steel. So you get the steel is replaced with the of 20 mm as a steel thickness into equivalent concrete mm thickness as 135. Okay, so therefore the thickness is added on both sides. Okay, internal diameter is 280 and equivalent thickness instead of 20 it is 135.23 into 2, so you get a total thickness rounded to 550 mm. Okay, so this is how the section is converted into a equivalent single material here in terms of concrete. Now find out the I values. Pi d4 by 64. Okay, and here diameter is 550, so 0.55 meter. So we get I value here 0.00449. So equivalent concrete EI, you know the E and I, so multiply these two values, so you get 132816 kilonewton meter square. Now calculate the stiffness. So all these exercise is done to determine the thickness T value, relative stiffness factor. So EI upon the coefficient of subgrade reaction 1/5. So finally T value calculated as 1.886 meter. Okay, again check for the a long pile. Calculate Z. So the T value calculated here, and check Z as L by T. Length of the pile is 20 and Z is 1.886, so it is 10.6, so greater than 5, so it is a long pile. Okay, and now the deflection is given 7 mm. Okay, and maximum deflection takes place at the surface, so that is 0. So what is the QG? Now there is no moment given and it is a free head condition, Therefore y is equal to ay qg t cube upon em. Second part is 0 because the external moment is given 0 and it is precondition. So therefore substituting these values, 7 by 1000 2.435, okay, and substitute t value 1.886 and ei values calculated earlier. So from this we get qg is 56.91. Now second part is what is the maximum under the free head condition, what is the maximum bending moment at this load? That was the question asked. You can see here what is the maximum bending moment for this load. Okay. Now we know the equation mx is equal to am qg plus bm mg, okay, and max here m value is 0, therefore mx is equal to am into qg, okay, because second term is 0 in a free head, it is a free head conditions. So you have to find out the am value. Now you can see the for maximum bending moment am should be a maximum from the table. Okay, you select the am value such that it is the maximum value. So for that let us refer the table. So if now you are referring the table and you will find that these are the am values, okay, these are the am values, and c is from the top z is 0, z is increasing 0.1 0.2 0.3, okay, and c it is increasing, the value is increasing 0.27 76 0.772 and 746 696. So 0.772 is the maximum value of am, and the corresponding the for 772 the z value is taken at 1.2, okay. So at 1.2 this value is maximum. So the value we got it at 0.772, and z value at that time, just confirm from this, it is a 1.4, okay, not 1.2. So therefore this z value is 1.4, at which the am is maximum 0.772. So substituting that value here, am into given qg value 56.91, so we get maximum moment as 43.93 kilonewton meter, and it takes place at z is equal to 1.4. So z is x by t, therefore x is equal to 1.4 into t, 1.886. So it is 2.64 meter below the pile head, that is from ground level. So at 2.64 meter the bending moment is maximum, that is 43.93. And next part is that the question asked is what is the value allowable load if the pile head is fully fixed, allowable load if the pile head is 50% fixed. Let us start with the D first. So partly fixed pile, you know the expression ay minus 0.93 lambda into by, okay. So it is the fixity is given 50%, so therefore by lambda is given as 0.5, okay, and value of deflection is maximum at the surface, that is a which is already given. For this surface deflection, ay is 2.435, by is 1.623, again from this table, that is at z is equal to 0, okay. I'll write this. So substituting this value, and give for a, this is for a given deflection. You have to find out the qg value. T value is given 1.886 cube, EY is there, so you can calculate is 82.59. Okay, so you can see here the value is increased as compared to the free condition. In a free condition, the value was 56 kilonewton, here it is 82 kilonewton. And for fully fixed pile, earlier parts, fully fixed pile means the same equation, the lambda value is 1. So when you substitute the lambda value is 1, unknown is qg, yx is again 7 mm is given. So if you calculate qg, it is 150. Okay, so when it is fully fixed means at the top of head is resistance against the rotation, the qg value increases. Okay, so in this way the lateral load can obtained for a different conditions. Okay, so here we discuss mostly the all bending moment and deflection at ground surface. In one numerical we find out what is the maximum bending moment. That time we required that entire values in the table. Okay, so similarly the any moment can be calculated at different depth. Okay, so the methodology is the same, only you have to refer the table and substitute the values. Most important thing is that when it is a fixed pile, that time this moment, external moment, even though it is given, it is replaced by the that mg value, that is minus 0.93 qg. Okay, so with this laterally loaded pile in a cohesionless soil, this part is over.